Hi, welcome back to KIG1015 Dynamics. Today we will look into kinematics of rigid bodies, but this time we are looking into how to determine or analyze on the accelerations of rigid bodies undergoing different types of motions, the translations, rotation about a fixed axis, and the general plane motions, like what we have covered earlier in velocity analysis. So this is the outline of today's lectures. We will recap back what we have covered earlier in velocity analysis. What are the available motions in rigid bodies in terms of translations, how to determine the velocity as well as the accelerations. When rotations about a fixed axis of a rigid body, what is its accelerations, then we will also look into how if it's these rotations can be represented by slabs, right, from planes where it rotates about perpendicular to this top view of that planes. We also look into recap back what's the equations before we move towards general plane motions. We learn that these general plane motions of a rigid body can be replaced by the translations about an arbitrary reference point and rotation about that reference point itself. So here we want to see how to determine now the accelerations of these rigid bodies undergoing general plane motions. So we also covered the concept of absolutes and relative accelerations in plane motions. Similarly, like what we have covered in velocity analysis, is one of the approach that we can use to solve or to determine these kinematics parameters, either is velocities or accelerations. And some of the plane motions, it can be directly determined in terms of its parameters, and we also will look into this. So recap back, kinematics of rigid bodies, relationships between the times and the position, the velocities and accelerations of a particle forming these rigid bodies. We have covered how to determine velocities of a rigid bodies. Then today we want to determine how the accelerations can be obtained when this rigid body undergoing different types of motions. So the rigid body motion, again, we have these translations. So rectilinear translation and curvilinear translations. We also have rotation about fixed axis, general plane motions. Okay, these three are our main focus. Of course, we have other types of motion which not fall into here, general motions or motions about a fixed point, some sorts like this. So, but our focus here is translations, rotation about fixed axis, and general plane motions. Why we cover these two, translation and rotations about fixed axis, because we can say that general plane motion can be expressed or replaced by translations plus rotations about fixed axis. Earlier, we have discussed and derived out the velocities and the accelerations of rigid bodies undergoing translations. So if we consider a rigid body in translations, so we are saying that the direction of any straight lines inside the body is constant, and all particles forming the body move in parallel lines. All right. So in this case, we have two particles in the bodies. Then making use of the relative position vectors, then we can get the velocity is constant over all particles having the same velocity, as well as the acceleration. So here we can say that if a body undergoing a translations, the velocities as well as the accelerations are constant for all the point of particles basically inside these rigid bodies. When we look into a rotation about a fixed axis of a rigid bodies, we also derive that when it is rotated about a fixed axis, right, you have the velocities equals to omega, which is the angular velocity, crossed with the positions vectors r. So v is magnitude will be v equals to r omega, right? In this case, where omega is your angular velocities. We also derive the accelerations of a rigid body when it's rotated about a fixed axis. Here, there are two components under this the accelerations of these particles itself. It can be combinations of two components. One is the tangential accelerations components, where it's related or associated with this angular accelerations. Then we have this alpha cross r. Then we also have the radial acceleration components, which is omega cross r, which is basically negative omega square r, which is the amplitude itself. So here we are saying that when the rigid body is rotated about a fixed axis, then the velocity equals to r omega, where omega is angular velocities. Then accelerations of that particular rigid bodies itself is basically have two components. One is omega square r, which is negative omega square r, which is the radial acceleration components. Another one is alpha r, which is associated with these angular accelerations. If we make use of the concept or the principle that we have discussed earlier on rotations about a fixed axis, and now we look into how if these particular bodies, okay, is rotates about axis perpendicular to this particular plane itself, we call it representative slabs. So basically, how if it's a plane, okay, then it is rotates about this axis that perpendicular to this particular surface itself. So we have these velocities against of any points of the slab itself. In this case, is p is equals to r omega. Okay, then we know that this velocity is going perpendicular to this position itself. Whereas the accelerations of any point P of this slab itself, you have again the two components. The first one is the alpha r, all right, which is perpendicular to your r, which is associated with this angular accelerations. Another one is negative omega square r, which is our normal components moving towards the center of the rotations. So we have the tangential accelerations, the magnitude is r alpha, the normal acceleration, the magnitude is r omega square. And we also discussed earlier in velocities topics, the omega, right, is positive, the angular velocity is positive and is counterclockwise. Same with the alpha, or what we call the angular acceleration, is positive and it is counterclockwise. When they are rotates in clockwise, then we have a negative sign. We also derive the kinematic equations that defining the rotations of a rigid body about a fixed axis. So it's similarly like what we have derived earlier in kinematics of rectilinear motions. So now it's in rotations. So in the positions now is referring to the theta angular coordinates. Then we have the velocities component is omega angular velocity. The acceleration components parameters now is replaced by alpha angular accelerations. So using the the equations or the relationship that we have derived earlier, then we can form under uniform rotations when your omega is constant, alpha equal to 0, then we have these uniform rotations equations. Then under uniformly accelerated rotations, when alpha is constant, we have a constant angular accelerations. Then we have another three kinematics so-called equations that basically describing the rotation of a rigid body about a fixed axis. Right, so they are similar to what we have derived in kinematics of rectilinear motions earlier in the beginning of this course. Just that now the parameters, our x is replaced by theta, our v is replaced by omega angular velocities, and our a is replaced by the alpha angular accelerations. If the slabs or the rigid body undergoing general plane motions, like what we have discussed earlier, this general plane motion can be replaced by translations plus rotations about a arbitrary or fixed reference. Right, so earlier we have making use of the absolute and relative velocities relationships. We have this VB equals to VA plus VB over A, right? So similarly, we have also absolute accelerations of particles at any point of these slabs equals to here AB equals to AA when it's undergoing a translation with A plus AB over A, and we have these rotations about A. And we understand that when it's rotations about a fixed axis about A, so we have this so-called acceleration under two components. In this case, we have the tangential and the normal components. So these AB or A can be resolved in terms of tangential and normal components. The tangential is alpha K cross R B over A, then AB over A N, which is a normal normals accelerations will be equals to negative omega square R B over A. Right, the magnitude is R alpha and R omega square. So to determine for example, the absolute accelerations of B, then given the accelerations of A and the angular velocity, how it is rotates with the angular acceleration also, we also will know, right, when this B rotates about a fixed axis A, then we have two components here, the tangential ABA T and ABA N, the tangential and normal components, and our actual ABA will be going here. So using this equation, we can solve the acceleration informations through vector methods or the diagram methods, similar like what we have learned in velocities diagrams. So in this case, our accelerations or relative acceleration will have two components. So it is what we call the vector polygons diagrams that as you can see at here. Right, so we have AB equals to AA over AB over A. Right, so this AB over A is we have two components. This AB over A, which is this one. This is our AB over A. We have two components, which is tangentials going tangential to this R, perpendicular to the R. Then we have the normal going towards the center of the rotations. So we have the normal. So that basically gives us the relative accelerations, AB over A. So again, it can be we can make use of this polygon vector polygons to find the informations of the accelerations, or we can make use of this equation and through the vectors methods like what we have learned here to determine the acceleration informations. If we look at the similar the rods models that we have earlier in velocities, so now we want to determine its accelerations informations. If it's given, we have what we call these accelerations of a, right, and the velocity a, right. We will want to determine the acceleration b and its angular accelerations. So again, when this rod undergoing general plane motions, then it can be replaced by translation with a plus rotation about a. Or in the relative and absolute accelerations equation, it can be written as AB equals to AA plus ABOA. And we have learned that this ABOA, we have two components, the normal plus the tangential components. From the relative accelerations, AB over A, the normals component, we know that is what we call this VA square over L, right? Or we have this R or L omega square over L, which is here we have L omega square. So we can determine this AB over A, the normals components of relative accelerations through these angular velocities with the length of this beam itself, as well as how if the velocity is given. At the same time, we can also determine the tangential components is L alpha, or what we call the R alpha, which is A D equals to R alpha. In this case, is L alpha, but in this case, we do not know where is this A, B, or A, the tangential go. It can go in these directions or in these directions, because we are not known, okay, this knowing this the directions of these angular accelerations. Similarly, this B, the acceleration B, which is unknown, which we want to determine also, it could be going up or it could be going down. If you want to express these equations, AB equals to AA plus AB over A in the diagrams forms, then it basically will lead to 4 different vector polygons as you can show, can be shown here. Okay, 1 A, B, C, D at here. All right, and we only know if we given the A is moving to these directions to the right, and we only know the normal accelerations and relative accelerations moving towards this A itself is always moving towards the centers and it is in this direction. So in this case, we have AA, AB or AB or ANs. Okay, if you have want to have a close so-called vector polygons, then probably the tangential have to go here, right? And your tangential relative accelerations tangential is have to go here. Then your AB have to going downwards, right? So or another scenario is when your AA is going to here, right? Our AB have to coming down always, okay, going towards this particular angle at here, right? Then in this particular case, the tangential relative acceleration will go to upwards like this, okay, with the angles thetas. Then our AB is going upwards. All right. But another case, okay, this also will lead to another case when your AA is going to these directions, the acceleration A is going to this direction. AB over A, the normal, always have to go towards the centers of the rotations. Then in this case, the tangentials component is not too large, okay, and in this case it's very large, okay, then it lead to a positive or going upwards acceleration at B. But if it's not so large, then it will lead to a negative so-called going downwards acceleration at B, right? So these two conditions is depends on the intensity or the value of our tangential components. Then we have also one scenarios when your A acceleration is going to the left, then we have a very huge so-called large so-called the normal accelerations vectors, then a small what we call the tangential relative accelerations vectors, then it will lead to what we call here the AB going downwards, right? So there are four different scenarios that can lead to these so-called vector polygons. Here is a closed vector polygons, which make these equations AB equals to AA plus ABOA valid. So this vector result, we can say that it depends on the directions of AA. So first we need to know the AA directions, and then the relative magnitude of the direction as well as its magnitudes, right? The AA plus the normal components of these relative accelerations, A, B, O, A, N, where it is related to your omega or your velocities, all right? Angular velocity or angular or the absolute velocity at A. So if you want to know which closed loops of these vector polygons, then the A direction as magnitude must be given, then the normal so-called relative accelerations also must be known by providing this angular velocity omega. And these accelerations at B and as well as these angular accelerations alpha can then be obtained if we consider successively the x components and y components of the vectors as you shown, and in this diagram itself we consider the summations of x components of this vector and the y component of these vectors. Then with these two equations we can solve the two unknowns of AB and alpha. We take these so-called polygons, vector polygons A as an example. So assuming A is going to the right, then we know that AB or A, the normal, is going into these directions with the angle theta. Then to form a closed vector polygon, then the ABAT have to go here, then our AB will have to coming down. All right. So if we can making use of these equations, right? This equation basically represent this polygon itself, right? Or based on this equation itself, if you can find what we call successively the x and y component of these vectors, okay? X components here, our AB is 0. Then we have our AA in x components. Then we have our our so-called L omega square sine theta, which is in our so-called components. It can be decomposed into these components, right? And this can be also decomposed in these components. Then we can have our AA plus this component in x components minus these particular components, all right, then equals to 0. AB, we don't have horizontal components, x components. Then we have y components, negative so-called AB. Then we have the y components also going down from the normal relative accelerations, and we have also another negative y components from the tangentials. Then with these two equations, we have the two unknowns of AB and the alpha angular acceleration. Then we can solve for this AB and alpha. So either we are using the diagram itself, or we are using the vectors method itself. It can be solved for these unknowns acceleration informations. In the case of certain mechanisms, it is sometimes advantageous in such a case to determine the absolute velocities and the absolute accelerations of the various points of the mechanism directly. The components velocity and accelerations at a given point can be obtained by differentiating the coordinates x and y of that point. If we consider against the rod AB here, whose extremities slides respectively in horizontals and verticals directions. Then we have these coordinates xa and yb of these extremities of the rods, and it can be expressed in terms of the angles theta the rod forms with the verticals. Then it will give us xa equal to L sine theta, yb equals to L cos theta. If we can differentiate this theta with respect to t, then we have the velocities va or x dot a equals to L theta dot cos theta. Right, this theta dot is also can be written as angular velocities, L omega cos theta. Whereas our VB here is y dot b. Differentiate this, then we have also negative L theta dot sine theta, or we can write it as a negative L omega sine theta. This velocity informations is also similar to what we have derived earlier in our velocities analysis topics through the vector methods, diagram methods of these relative velocity and absolute velocity equations, or through this instantaneous center of rotations methods. So both also will give us the velocity information as you can show here. So this one is directly differentiated from the what we call the coordinates or of the positions x and y. If we differentiate against, then we will give us this acceleration information or x double dots a. We differentiate this again, then will give us this negative L omega square sine theta plus L alpha cos theta for the accelerations a, and acceleration b, which is a y double dot or v dot, is equals to negative L theta dot square cos theta minus L theta double dot sine theta, or it can be written as a negative L omega square cos theta minus L alpha sine theta. And again, these accelerations informations of this rod A and B are similar, right, with what we have derived earlier using these vectors methods, the vector, the polygon vectors methods through these absolutes and relative accelerations equations. So they are basically the same. So in this particular case, if this yb or xa is known, particularly on this type of mechanism, then it can be easily determines the velocity information, acceleration information directly, from the position or xa, yb. So we do not really need to go through these absolute relative velocities equation or the absolute or relative acceleration equations through this vector or the diagram methods to determine these velocity or acceleration informations. Right, so this is certain cases we can directly determine, right? Not all cases, only certain cases where this position information is given or known. In summaries, in these topics, we learned how to determines these accelerations informations from rigid bodies undergoing particularly on general plane motions. We also from there we know that it is replaced by translations and also a rotation about fixed axis. So through these relative and also absolute accelerations methods, we can use either in the equations vector methods to solve it, or the diagram methods to solve for the accelerations informations. Similarly, like velocity analysis, during the velocity analysis, we are using the same approach, either with the velocity diagrams as well as the vectors methods through these relative and absolute velocities equations to solve for the velocity informations of this rigid body undergoing general plane motions. Under velocity analysis, we have another alternate methods, which is instantaneous center of rotation methods to determine the velocity informations. But this method is not applicable to acceleration analysis. We have also discussed earlier, accelerations it's not zero, okay, at that particular instantaneous center of rotation, because the velocities at zero at this instantaneous center of rotation is only at that particular instance. At different time instance, these basically the velocity will change at that particular center of rotations. Then you have accelerations, what we call non-zero accelerations. So remember, this instantaneous center of rotation method only applicable for velocity analysis, not acceleration analysis.